Hi lovely level 2s and welcome back to 2.4 Atomic Structure and Bonding, and today we're doing lesson 6 on ionic solids. And so let's get started. So I'll just actually flick back to the learning objectives. So today we are going to define the ionic bond, then we're going to describe the structure of the ionic solid, and then we're going to describe how that structure affects the physical properties. So really similar to metallic, but now we're talking about ionic. I personally think these are a little bit easier for students actually. So first of all, what is the ionic bond? So the ionic bond is that electrostatic attraction between oppositely charged ions, so between the cation and the anion. So that's the ionic bond. It's a very strong bond. And what is the ionic structure? So the structure of an ionic substance team is what we describe as being a rigid three-dimensional lattice, and you can see this diagram's three-dimensional, and I have to use diagrams because I am hopeless at drawing these. So a rigid three-dimensional lattice where cations are surrounded by anions and anions are surrounded by cations. And what's quite significant here is these are actually directional bonds compared to before, and what that means is that this anion is fixed to this cation and this cation and this cation, and they're locked in that position, and that's what that rigid is referring to. Okay, that those ions are locked in their place surrounded by oppositely charged ions. So this is an example of sodium chloride. We've seen one in the previous slide. Just a bit of a recap that an ionic bond forms between a metal and a non-metal, and it's via the transfer of electrons. So metals donate electrons to non-metals which accept them, and when a metal loses an electron, there are now more positive protons than there are negative electrons, and that gives it a positive charge. And negative ions have a negative charge because there are more negative electrons than there are positive protons. Okay, so let's just run through some stuff. So I've done like a wee prior knowledge from the other lesson. Why is it that table salt dissolves? I'd love it if you could pause your video, and even if you say it out loud, even if your family think you're bonkers, as to why sodium chloride dissolves, and then I'll give you the answer now and you can check how you did. So solubility, so why does it dissolve? So it dissolves because there are electrostatic attractions between the positive sodium ions and the negative oxygen atoms in water, and the negative ions are electrostatically attracted to the positive hydrogen atoms in water. And these attractions between the waters and the ions are stronger than the ionic bonds that are holding it together, and that's why it dissolves. So hopefully you got that. I'm really emphasizing a common mistake that kids make is they say the hydrogen ions or the hydrogen or the oxygen ions instead of the atoms in water, because remember, water is a covalent molecule, so all of the these are all atoms, not ions. So that's just a technicality. Make sure you don't fall into that trap. So when something actually dissolves, this is going beyond what you need for level 2, but I think it's super interesting. There's a certain number of waters that naturally can fit around an ion, and a lot of the time it's 6. So both sodium and chloride can have 6 waters surrounding them, and we use the term aqueous. So AQ is for when something is dissolved in water, okay, which most of you know, and these are actually hexahydrate ions, and that's because 6 waters surround those ions. That's pretty cool. So if you actually wanted to be technically correct, but you will not be asked this in your exam, that's actually what the ions look like in water. Oops. Yeah, and so there's 6 waters surrounding the sodium, and that's why this has got a positive charge, and there's 6 waters surrounding the chloride, and that's why it's got a positive charge. Don't need to know for your exam, but it's interesting. So this is dissolving ionic solids, and this is kind of me just putting it into writing. You're going to be so bored of this. So if the ionic bonds are overcome by the attraction of the ions to the polar water molecules, then the ionic bond is weaker than the attraction of the ions for water. So that's just saying that the attraction has to be weaker between the ions if it's going to dissolve. The positive ions are surrounded by the negative oxygen atoms, and the negative ions are surrounded by the positive hydrogen atoms. Yeah, cool. Hopefully that makes sense. Yeah, and what if they're not soluble? So if something's not soluble, it's insoluble. Okay, and that happens when the ionic bond is stronger than the attraction for the water molecules, and that does happen, but they'll specify in your exam what they're wanting you to discuss. It'll make total sense. You don't have to memorize certain ionic compounds at all. So electrical conductivity. So team, we know that to conduct electricity there must be free moving charged particles, which are either ions or electrons. That's a wee parrot sentence that you're going to learn from me. So here's a solid ionic lattice. Now solids cannot conduct because even though there are charged particles, all these positive and negative ions, they're in that rigid lattice and they're locked in a fixed position. And that means that they cannot move. So solid salt doesn't conduct. If we had a power supply here and a light bulb, I could get the table salts out and plug it in and you would see that no light bulb would go. However, if we heat up this solid sodium chloride, for instance, in like a big metal barrel and heat it up really high, like hundreds of degrees, and turned it into molten means liquid, then that structure's broken down and you can see that all of these ions can therefore move. And if the ions can move, then they can conduct electricity. And you'll notice here that the positive ions gravitate towards the negative electrode and the negative electrode ions gravitate towards the positive electrode. You won't be asked to explain that. That's just another example of electrostatic. Okay, so molten, what you need to realize is that the structure breaks down and the ions can move. Now, just the same as if we actually dissolved it in water, it actually does the same thing. So if we formed an aqueous solution, so we popped that ionic solid in water, it no longer has that structure, but takes on this structure where the lattice is broken down and we know that all these ions are surrounded by water molecules, but they're actually still able to move. So both in molten and aqueous solutions, ionic substances can conduct, but not in the solid state. And so you just have to link it back to the particle we're talking about. For ionic are ions, okay? They cannot move in the solid state, but they can in the molten or aqueous. If we were testing the conductivity of ions, this is known as an electrolytic cell, which uses a power supply. And you don't need to know what I'm saying, but this is a level 3 concept. And it uses electrodes, and you can put, and they've connected a bulb here, and you can put various solutions in this beaker to see if that bulb will go. And if we put NaCl in here, you would see that the bulb lights up, and that's because it dissolves in water, and so the chloride ions will travel towards the positive terminal and the sodium ions will travel to the negative terminal. This is not assessed at level 2, but that's what we mean by conducting an aqueous solution. Well, this is super interesting. So condoms are actually tested via conductivity. So what happens is you can see down here, that's actually a big container filled with sodium chloride. Now what they do is they fill up a condom filled with water. Now pure water does not conduct, okay, so it will not conduct. Pure water will not conduct. And so when they dip these into this tub of sodium chloride, nothing should effectively happen because if there's no leak in the condom, then you've got the rubber condom is an insulator. And so that means that none of the sodium chloride can reach the terminal, which is in here, to sound an alarm. However, if there is a leak in that condom, then that means that sodium chloride in the tub will go into the condom and it'll reach the terminals that are up here and it'll sound an alarm, and that's because sodium chloride conducts. So this is actually how they test condoms, and they'll use like a rating of out of how many 100 condoms this many sounded the alarm. So yeah, pretty interesting, I thought. So ionic solids are brittle. So what does brittle mean? So brittle is referring to if you hit it, what happens to that substance. And if you hit an ionic crystal, an ionic lattice, with like a hammer, it doesn't even need to be a hammer, with anything, the end of a knife, like if you went and got some salt and put it on a chopping board and you smacked it with the back of a heavy knife, it would shatter. And that's what brittle means. And the reason why, guys, is if you look at this diagram, it's great. They're saying if you put a blow here to hit the top of this lattice, what would happen is you'd push this top bit down. Cations would get in contact with cations, and anions would get in contact with anions. And we know like charges repel. And so this whole thing would repel and shatter. Okay, and that's a really important property of ionic solids. So that is that if a force is applied, okay, cations come in contact with cations and anions come in contact with anions, they repel and it causes the structure to be to shatter, and that's what brittle means. The other thing here is that hardness, okay, they're technically hard because they're quite hard to kind of it's quite a firm structure without being hit with something, and that's purely because the ionic bonds are strong. Okay, so strong bonds make it hard, but this brittle one is the property that you're most likely to be asked about. Melting and boiling points. Well, this one's nice and easy, and if you look at this table down below, so here are some ionic compounds, and you can see here that the melting points we're talking about and boiling points are in the thousands and melting points are in the hundreds. They're really high. So why are they high? Because they take a lot of energy to break. And why is that? Because the ionic bonds are strong. So melting points are actually one of the easiest to actually talk about. Like, for instance, sodium chloride doesn't melt until 800 degrees. And that's purely because the ionic bonds are super strong and they take heaps of energy to break. Yeah. Oh, and this is quite cool. The higher the charge of the ion, the higher the melting point. And that's because the electrostatic attractions are stronger. So that's the same as metallic bonds. So a metallic bond with a 2+ charge is stronger than a 1+ charge, and that's the same as here. Okay, so it does a similar thing. Okay, so ionic solids are described as not being volatile. I realize a few of you won't probably know what volatile means. Volatility is referring to whether something can easily turn into a gas. And if things easily turn into a gas, they're quite smelly. And most don't have a smell, and so ionic solids are not volatile. I think I've only got a little bit to finish on here, folks, and that's just to talk about the most reactive metal and the most reactive non-metal, because they'll form ionic compounds, and this doesn't really fit here all that well. It's just kind of an interesting tidbit. The most reactive metals that we'll be talking about is actually the bottom here of group 1. Because one electron's very easy to lose, and down the bottom here you've got the most number of energy levels, and here your most reactive non-metal, we ignore these guys because they're not reactive. Your most reactive non-metal is going to be your fluorine, which is up here, and that's because it wants one electron, okay, and it's the smallest. Okay, so that's just there. Cool, so here's a wee summary table again, and I actually might start on this at the start of the next video, so hold tight, I'll see you soon, team.